Right, now let's move to the final two questions of the third worksheet. Now these two questions are a little bit tricky. The important part here in this problem is, now first let me write down the problem. That is the limit of x goes to 0 from the positive side of x to the power 2x. So the important point here in this question is you have an x term in the base as well as in the power. Now when you have a situation like this, you are not allowed to compute the limit of the base and then take it to the power like this. You are not allowed to do some computation like this. Okay, so even though if you did that, you will end up with a situation like this, but it is not at all a good practice to distribute a limit to both base and the power when you have the variable in both base and in the power. But say for instance, if you have something like this, if you have a number in the base and the variable on the power, then if you are supposed to compute the limit, then of course you can just distribute the limit to the power, because that's the only place where you have the variable. And in fact also you can do it the other way. If you have the variable in the base and a number in the power, you can just distribute the limit for the base only and keep the power as it is. But whenever you have the variable in both base and the power, you are not allowed to do so. Okay, so the trick here we can use is with applying logarithm. Right, now let me rewrite the question one more time. Here, in order to compute this problem x to the power 2x, what we can do is we are using some standard method, right, which is we directly apply the logarithm of this number. You will see why it becomes an easy tool when you have the answer for this logarithm of this whole thing. Okay, now by using logarithm tools or logarithm techniques, we can simplify this term a little further, which becomes ln x, because we have the logarithm rule where log a b to the power c is equal to c times log a base a of b. Okay, so that's the logarithm rule that we have applied here. Then we can try to compute the limit of this term. Now keep in mind that this is not equal to the logarithm term, right? Now the original problem was this one, and we just computed without any relationship, we just computed the logarithm, and now we are trying to find the limit of this new problem. But keep in mind that this is not equal to this one. Okay, so and later on you will see how we can relate the answer of this one to the original required sum, right? Okay, so if we compute the limit of this logarithm term, then it will be x to the power 2x, and that is the limit of x goes to infinity 2x ln x, right? and sorry, it's not infinity, it is 0, right? Now, and see, in the very original problem, they have given the limit as 0 plus, which is the right hand side. And if I can remember correctly, we discussed this right hand side limit in the first video of this session, right? That there I explained it is because of this ln x term, right? So this limit makes sense. But because if you had a left hand limit, and if there is the ln x term, then there will be a problem because the domain of ln x is in the positive real number set, right? Okay, anyway, now if you try to compute this limit, you will end up with the 0 times infinity situation. Then, therefore, what we can do is we can rearrange these terms as we did before in order to apply the L'Hopital's rule, right? So what we can do is we can rearrange the term like this, ln x over 1 divided by x, right? And then if we try to compute the limit of this one, you will get 2 times negative infinity, sorry, this should be positive 2, times negative infinity because ln 0 is negative infinity, over 1 over 0, which is infinity. So basically what we have is negative infinity over infinity. That means we can apply the L'Hopital's rule for this one. So how do we apply the L'Hopital's rule? The derivative of the same limit you can obtain from the L'Hopital's rule will tell you can obtain the same limit by, even though you have the derivatives of the numerator and the denominator. So when you differentiate the numerator, you will get this one. And when you differentiate the denominator, you will get this, right? So upon applying the limit, when you apply the limit, you will get this one. Now, before applying the limit, you can do some simplifications here. This is limit x goes to 0, 0 plus 2x, 2 divided by x. This is divided by negative 1 over x squared. So you can rewrite this term as 2 over x times x squared over negative 1. So basically what you will have is negative 2 times x. So basically this is equal to limit of x goes to 0, negative 2 times x will be equal to 0. And now we should see how we can relate the answer of the limit of this one to our original problem. So for that, we are using this formula. This is a standard formula which says when you raise e to the power ln fx, it gives you fx back. So following this relationship, this standard rule, if we need to get x to the power 2x, which is the original problem, we can rewrite it in terms of e raised to ln, and instead of fx we can write x to the power 2x. So this is the same as this one. That means computing the limit of this one, which is the original problem, computing the limit of this one is the same as computing the limit of this term. And to compute the limit of this term, you can see in the base you don't have a x term. That means in order to find the limit of this one, you can find the limit of this one. To compute the limit of this original problem, it is the same as compute the limit of this one. And since you don't have an x term in the base, it is the same as computing the limit, keeping the base as it is and computing the limit of the power. And see, in this section we have found the answer for the limit of this power, which is equal to 0. So it becomes e to the power 0 in turn gives you 1. That means the limit of this one is equal to the limit of this one, and the limit of this one is equal to 1. Which means the limit of this original problem should be equal to 1. Okay, then we'll move to the next, the final problem. It will also have the same shape as it was in the 5th question. So the last problem is limit of x goes to infinity, limit of 1 plus 1 over x to the power ln x. Now here also you can see you have a x term in the base and a x term in the power. So you can't just compute the limit of the base and raise to the limit of the power, because you have x in both base and the power. Now therefore we can use the same standard technique as it was before, which means we compute the logarithm 1 plus 1 over x ln x, and that is equal to ln x times ln 1 plus 1 over x. This is the logarithm rule. Logarithm of base a to c is equal to c log b a. This is a, and according to this question, c represents this one and this term represents this one. ln means log base e. Right. Then if we try to compute the limit, you can see the limit of this when x goes to infinity will be infinity, because the graph of ln curve will be something like this. So x goes to infinity, the ln term will eventually reach infinity far ahead of this x-axis. Right, so this becomes infinity, and this is in, if this is infinity, this term will be 0, so ln 1 will be 0. That means you have come to an indeterminate state, and we can see whether we can apply the L'Hopital's rule. Now, to apply the L'Hopital's rule, we should make some rearrangements. So the way we can rearrange the problem is like this. We can have the denominator to be 1 over ln x. Now keep in mind, you cannot change the original problem. So if you write the terms like this, it is not the same question that they have given. So you cannot change the original problems, okay? But in this rearrangement, it yields out the same question, okay? Right. Now for this one, if you calculate the upper and lower limits, you will end up with the 0 over 0 situation. So we can apply the L'Hopital's rule. And when you differentiate numerator and the denominator, how are we going to differentiate it? For the numerator, we have a situation like this, logarithm of a certain function, and if you differentiate it, you will get f prime x divided by fx. And in the denominator, what we have is, you can write the denominator as this, right? The denominator was 1 ln x. This whole term, we should consider this whole term as the denominator, and we have to differentiate this whole term. So we can write it like this. In fact, in the general form, this we can see as a function of this particular format, fx raised to the power n. And in this type of problems, if we have to differentiate it, you have the standard rule, fxn minus 1 times f prime x, right? So to differentiate the denominator, you will have to use this result, and to differentiate the numerator, you will have to use this particular result. So upon differentiation, you will end up with, if you do the differentiation correctly, you can get, okay, let me calculate the derivatives. So to calculate the derivative of this one, we need this thing, right? F prime x. So here for the denominator part, you should have the original term fx and the derivative of this, which is minus 1 over x squared, right? And in the denominator, we should get minus, we will have minus 1, see, the power n represents negative 1, ln x minus 2, because n is negative 1, times 1 over x. So this is the derivative of this term, differentiated according to this rule, right? So there we will have negative ln x raised to power 2 divided by 1 over x. And then when you can simplify it a little further. Well, what we can do is we can rewrite these terms like this: negative 1 over x squared over 1 plus 1 over x divided by negative ln x. Sorry, this should be negative ln x to the negative 1, 2 over x, right? And here you can simplify it further. You have this one here in the top, and for the denominator you can take it to the same term, same denominator, this term. This is x plus 1 over x. This is, since it is division, I'll rewrite it like this. I'll write it as it is. And here we will have negative 1 over x times ln x squared. Okay? Because here you have negative 2, and when you take it down, it becomes positive. Right? And then what we can do is we can have this term simplified a little more. Minus 1 over x squared times this is divided by this one, that means multiplied by the reciprocal, which means x over x plus 1. This is the term corresponding to this one. And then for the other part, you can write it as a multiplication ln x squared over negative 1. And then when you cancel the terms, you can get ln x squared over x plus 1. So, but the thing is, again, now this is the first stage of L'Hopital's rule. I mean the first this is the original problem, and we have applied the L'Hopital's rule for the first time in this problem. Now, but the thing is, even for this stage, when you compute the limit, you will again get the infinity over infinity situation. That means we can reapply the L'Hopital's rule for this first stage. Now, for the second time, we are applying the L'Hopital's rule. And then, when you apply the L'Hopital's rule for this function or this quotient, you will have 2 ln x 1 over x over 1, right? So now we can easily compute the limit of this simplified term. But still we are not finished, okay? Now here what we have done is, we had the original problem. In the original problem we were supposed to compute the limit of this one, but instead we computed the limit of this one, which is the, now here this is the limit and this is the logarithm, okay? Now we computed the limit of the logarithm of this, right? So what is the mathematical trick that we can use here? E to the power ln fx is equal to fx. So instead of computing the limit of this one, we should compute the limit of this. Now if fx is equal to this, with this whole term, if this is our fx, then the limit of fx, which is our original problem, is the same as the limit of this one. So the limit of this is equal to the limit of e fx, right? And e ln fx, right? And we have calculated the limit of e ln fx as 0, right? That means this is equal to e limit of ln fx is equal to e0, and that is equal to 1. Basically, that means ultimately we can conclude that the limit of this one is equal to the limit of this one is equal to the limit of this to the power limit. Limit of this one is equal to the limit of this one, and that is equal to e raised to the power of this, which has a limit, and we computed that limit separately.